Today's lecture is about the Jacobian matrix. We use the Jacobian matrix to find the velocity of an end effector. If you took linear algebra, you might have already learned how to find a Jacobian matrix, and if so, that will be very useful to you. If not, I'll show you how to find it in this lecture. We'll also talk about how you use it in robotics to find and set the velocity of your robot's end effector. To begin with, I'm going to introduce some new notation. This is the Greek letter chi, and when we're looking at the velocity of an end effector, the letter chi is going to be representative of the velocity of our end effector in the base frame. Now, the velocity of the end effector in the base frame has two components. The first component is the linear velocity of the end effector, and the second component is the rotational velocity of the end effector. I'm going to pause in the notation for a moment and talk about what this means when we split up the velocity into linear and rotational components. Let's suppose that you have a joint that is attached to the ground, and attached to this joint is a single link. I'm going to draw two coordinate frames. A base coordinate frame that's attached to the ground, and a second coordinate frame that is attached to my link. I'm going to say that the angle of this link is theta. Each of these coordinate frames has a center, and this center is usually represented by the letter O with a subscript for which frame it belongs to. So this is O1, the center of frame 1, and this is O0, the center of frame 0. Back when you started studying physics, or the first kinematics class you would have taken, you probably learned how to find the linear velocity of point O1. You would have learned that the velocity of O1 is equal to omega cross r, where omega is equal to theta dot, and r is the length of this link. Rather than thinking of omega simply as the derivative of theta, we can also think of omega as being the rotational velocity of frame 1. V is the linear velocity of frame 1, by which we mean the velocity of the center point of this frame. But the center point is not the only thing that moves. The whole frame also rotates. Theta dot is the speed at which this frame 1 rotates around the axis, either Z1 or Z0. Thinking, since these two axes are parallel, you can think about it either way. But in either case, we have two components to this velocity: the linear velocity of the center point of the frame, and omega, the rotational velocity of the frame 1. So going back to our notation, as we try to represent the velocity of the end effector in its base frame, we want to allow for any number of links in 3 dimensions. So this This chi notation accounts for both the linear velocity of frame n, which in this case will be the frame of our end effector, relative to the base frame, and omega is the rotational velocity of frame n, the end effector frame, relative to frame 0. Now, before we move on and look at some additional notation, think for a moment about what the size of this vector will be. The way it's written here, it looks like it has only 2 components, but that isn't quite true. Remember that we're working in 3 dimensions. So the linear velocity has 3 components: an x component, a y component, and a z component. And omega also has 3 components: a rotation about x, a rotation about y, and a rotation about z. So here is what this expanded vector looks like. It has 6 rows and 1 column, expressing the velocity of the end effector relative to the base frame. Now, here's a second important piece of notation. We write this as q dot. Q is a generalization of our joint variables. So for each revolute joint, Q is theta for that joint. For any prismatic joint, Q is the displacement of the joint, d. Q dot, then, is the time derivative of each joint variable. Q dot is also a vector. It has 1 column, and it has a number of rows equal to the number of joints. If we have an articulated manipulator, the kind of manipulator we looked at in class last time, we have 3 revolute joints. So we have 3 thetas, and Q dot will be expanded as theta 1 dot, theta 2 dot, theta 3 dot. If we had a 6 degree of freedom manipulator in which all of the joints were revolute joints, then Q dot would have 6 rows and 1 column. It would have 1 row for each theta. If we had a prismatic joint, let's say that the 3rd joint of a 3 degree of freedom manipulator was a prismatic joint, instead of theta 3, we would have d, the displacement of that joint, the time derivative of it. Now that we understand the meaning of chi and q dot, we can write the key important equation for velocity kinematics of a manipulator, and it looks like this. Chi is equal to the Jacobian matrix times q dot. So the Jacobian matrix is the matrix that transforms the joint velocities q dot into the end effector velocities chi. If we know the Jacobian matrix, then we can specify joint velocities and find out what our end effector velocities will be. Or we can do it the other way by inverting the Jacobian matrix. We can specify velocities that we want for the end effector, and we can find the joint velocities that will give us those end effector velocities. In the next part of this video, we will look at how to find the Jacobian matrix.